Hi, everyone. So I am back to do another video on polar coordinates this time in our Calculus 3 course. So let's jump into it. We have 5 objectives in this lesson. The first one being plotting points using polar coordinates. The second being converting from polar coordinates to rectangular coordinates. The third, vice versa, rectangular coordinates to polar coordinates. Fourth, transforming equations between polar and rectangular forms. And then our last objective, being able to identify and graph polar equations by converting to rectangular equations. There are, I believe, 13 examples in this lesson, so we're going to get loads of concrete examples and practice throughout this next 1 to 2 hours. And then we have some note slides as well, so that you guys have a good grasp of the definitions and the concepts. Okay. So first note slide, we've seen this all before. A coordinate system, our XY coordinate plane. So I'm not gonna read this slide word for word. I'll have you guys do that for me. But this is just to sort of refresh your memory on, okay, when we're looking at a rectangular coordinate system, we are dealing with our good old X and Y axis and coordinate plane. However, a polar coordinate system involves angles. And so when we're looking at any sort of angle, right, we have an infinite number of angles with all of our infinite coterminal angles. And so what's the shape that goes on forever and has no end? A circle. And so when we look at a polar coordinate system, we're actually going to have these like concentric circles that are taking place and stemming from the origin to represent your distance out from that origin, and then to also give us a nice playing field to plot our proper angle measure. Right? Let's continue. I guess I'll read this whole little blurb here so that we can look at some new vocabulary words, our pole and our polar axis. So we have a polar coordinate system is constructed by selecting a point O, which is stemmed at our origin in this case, called the pole, and a ray with its vertex at the pole in order for us to create that angle, called the polar axis. So right now we're looking at an angle of 0 degrees, but then if we took that sort of hand and then created an angle, we can have a nice 45-degree angle over here, once again stemming from that pole. It's customary to have the pole coincide with the origin and the polar axis to coincide with the positive x-axis of the rectangular coordinate system. Okay, so let's keep going. This is kind of what I was demonstrating with my hands a little earlier when we create an angle stemming from that x, that positive x-axis, also known as our polar axis. And then our r is telling us what our, oops, sorry about that. Our r is our radius, our distance that we are dealing with from our initial starting point. So in polar coordinate form, we have our coordinate represented by r comma theta, our radius comma our angle measure. I'll highlight this up here as well. All right. So we have A point P on the polar coordinate system is located by giving the directed distance r, aka our radius, from our origin, aka our pole O, to a point P on our polar coordinate plane, and the angle theta from the positive x-axis, also known as our polar axis, to the ray OP. Just as a rectangular grid is used to plot points given by rectangular coordinates, a polar grid is used to plot points given by polar coordinates. A polar grid consists of concentric circles. I hope I'm pronouncing that correctly. Concentric. I think it's concentric circles centered at the pole and of rays with vertices at the pole as shown in the figure below. So again, these concentric circles tell us, okay, we are 1 unit away from that starting point. 2, 3, 4. It's how we can determine what our radius is. And so I kind of did like a general example here. This is our point O. We have our point P. So this is our ray OP with our radius. Our radius here is 2 units, right? One concentric circle, another one, and then it's that point P lies on that second one. And then our theta is the angle measure between that terminal side, aka our ray OP, and our polar axis, aka our positive x-axis, right? And so we know distance is always positive, but when we are looking at our R value, we could have a negative R, which sort of tells us that it's stemming in the opposite direction. And so if our R is positive, then our point P lies on our terminal side of theta. But if it's negative, then it lies on the ray pointing in the opposite direction. But again, anytime we're asked what the radius is, whether R is positive or negative, our radius is always the absolute value of R because, again, distance is always positive. So we'll be doing a few concrete examples in a moment where our R value might be positive, our R value might be negative, and then our angle measure might be positive, our angle measure might be negative. Remember, if our angle is negative, then we're going in that clockwise direction. And then we want to graph where this point pops up. This is just a numerical example, plotting out 2 comma pi over 4. Again, our radius, our R value is 2. And then our angle measure pi over 4, also known as 45 degrees. And then over here is just demonstrating this is if our R was positive, and then if it was negative, then we would be going in that opposite direction. Okay, so example 1, we have 4 different parts to this. We have, or we're being asked to plot the points with the following polar coordinates. And I put in sort of these graphs to just help us out a little bit. And so let's maybe zoom in so you could just see it a bit more clearly as we tackle part A. And again, when we're looking at polar coordinates, we have it in the form, our coordinate is in the form of r, comma, theta. So it's very clear that our r is 3 and our theta is 5 pi over 3, which if you wanted to convert that to degrees, that would be 300 degrees, because we know 6 pi over 3 is the same as 2 pi, which is 360, and pi over 3 is 60, so 360 minus 60 is just 300. So why don't we maybe write that on the top? We can. I personally like that. I mean, I'm good with fractions too, but I like the degrees as well. I don't know, my mind works better in degrees sometimes. However, I just like having both of them up there. Okay, so now we're ready to plot. 300 degrees. Well, if we zoom in on our polar coordinate plane, 300 degrees is going to lie in this fourth quadrant here. I'm just zooming in on that. And we know the fourth quadrant is 90 degrees. But if we cut that 90 into thirds, we have 30, 60, 90. So each sort of slice is 30 degrees. And if we know that one full rotation gives you 360, also known as 2 pi, and we want to subtract 60 to get 300, then 300 would be right up until this point. Okay, so I'm now going to erase the orange and maybe just put a little dot at that point. All right, at 11 pi over 6. Which, that doesn't seem right because 5 pi over 3 is 10 pi over 6. So our units, I think, are a bit off. Give me a second. Oh, no, it's not. I made a mistake. So it's not there because that's just 30 degrees. We want minus 60, so it would have been taking 2 slices away. So we're over here. Which, if I just looked at the graph, right, it has it very clearly labeled 5 pi over 3. All right, so now we're ready to plot it. I think I might stick with the orange because you guys could see it pretty clearly. So we stem from the origin, we're going all the way to 300, and now our radius is 3. So we, using our concentric circles, we want to go ahead and from the origin, go out 3 units. So this is 1, this is 2, and this is 3. So this is our point. And if we want to be a little more accurate, we can move the arrow so it's actually pointing there. So it's all the way out to here. And now we can draw out our line stemming from the origin. And we can write out r is equal to 3. So this coordinate point is, again, 3 comma 5 pi over 3. And we're done. Let's move on to part B, and now we can pick up the pace a little bit. So 2 comma negative pi over 4 is the same as 2 comma negative 45 degrees. And so that negative 45 is going to be going in that clockwise instead of counterclockwise direction. And so we want to cut this second quadrant in half exactly to hit that 45-degree marker. Let me see if I did that correctly. 1, 2, 3, 4, 4.5. 1, 2, 3, 4, 4.5. Good. So this is our negative pi over 4, which is also known as 7 pi over 8. And then our radius is positive 2. So go out 2, we have 1, we have 2. And so that coordinate point is simply 2 comma negative pi over 4. Right. And we are done. What I'll do is maybe I'll erase this part of the line and then I'll bring in the arrow a bit more. I'll fix that. Right, much better. Let's keep going. C, we want to plot 3, 0. So that one's going to be a nice easy one because our radius is 3, our degrees is 0. So we're just staying on that positive x-axis, and then we're going out 3 units. 1, 2, 3. And so we have 3, 0. And then I'll extend a line from the origin. And there it is. And then last but not least, our part D, we have -2, so our R is negative now, and then our angle measure is pi over 4. So 45 degrees. Once again, let me do the halfway marker, which is over here. And so I'll put a little dot there. So this is our pi over 4. And if we go out to here, 1, 2, this would be 2 comma pi over 4, but we want -2 for our R, so we're going to go in the opposite direction. So 1, 2, and then maybe I'll actually put, let's see, 1, 2, 3, 4. It's over here. Put that in. And then 1, 2. Orange, and then draw a line from the origin. And then coordinates. So we have -2 comma pi over 4. And there we have it. So we completed example 1. Now the next slide is sort of just the answer key that I created before. But what I also have is this is just another way of sketching out our part A if you didn't have a template. And so you create your X and Y axes, and then again, think about an imaginary circle so that you can plot that pi over 3, 5 pi over 3, which is 300 degrees, which is over here. And then from the origin, then you count out 3 units for your radius. So this would be your point. 3 comma 5 pi over 3. We're done. Okay. So let's keep going. This slide is just stating how there is a very big difference between our rectangular and polar coordinate form. Again, rectangular system, we're dealing with a good old plain XY axis, and angle measures aren't involved. You're just plotting X comma Y. Simple example, 5 comma 2. You go in the positive x-axis, 5 units, and then up 2 units, plot your point, done. There is no angle measure involved. And there is exactly each point in our rectangular coordinate system just corresponds to exactly 1 pair of rectangular points. And that's key because in a polar coordinate system, we have an infinitely number of polar coordinates. And again, that's because we're dealing with coterminal angles. Circle, our angle measures go on forever and ever and ever and ever. And so even though we have pi over 4, 45 degrees, 45 degrees is the same as 45 degrees plus 360, which is 405. So 45 and 405 land at the same exact point. In radians form, you're dealing with pi over 4 versus 9 pi over 4. They land in the same exact spot. And so down here, we have that representation. Polar coordinates are r comma theta. When we're dealing with our coterminal angles, we have theta plus 2 pi k. And then obviously, like we want our k to be an integer because then uh, it won't do the exact full rotation. Okay. All right. And then we can also look at it as the negative r value, so the opposite direction. So why don't I highlight this part? Polar coordinate, every point can be represented by an infinitely many or infinite number of polar coordinates, whereas rectangular system is fixed. We have just an exact pair. Okay. So this is our example 2. It's all written out for us. We have consider the point P with polar coordinates 2 comma pi over 4 because, oh wow, I used that same exact coterminal angle earlier when I was verbally talking to you guys. Because pi over 4, 9 pi over 4, negative 7 pi over 4 are all coterminal angles. They all have that same terminal side. This point also can be located by using the polar coordinates 2 comma 9 pi over 4, 2 comma negative 7 pi over 4, or 2 comma this should be 9 pi over 4. There's a little error here. Let me fix that. All right, that's better. I want to see if it's correct down here, though. And, um, no, that actually is correct. It's 5 pi over 4, but our R value should be negative. So that negative 2. And that's because I'll show you in a second. If we look down here, if we have 5 pi over 4, also known as 182.25, our angle is over here. And so we have our R is of distance 2, but we want it in the opposite direction. And so our opposite direction will give us that negative 2. And so we have it correct here. We just have the negative missing up here. And all of these are right. So yeah, this is just showing us that all of these points, even though they're different coordinates, they end up at the same exact P each time. Okay. Right, our second objective, we are going to practice converting between rectangular coordinates and polar coordinates. And so we have the conversion down here. This is just a comment saying that sometimes it's necessary to convert coordinates or equations from rectangular to polar form and then vice versa. So our third objective is going to be going from polar to rectangular coordinate form. And then we are, in order to do this, it's important to know that our x and y values in rectangular coordinates is the same as our r cosine theta and our r sine theta. So back in pre-calculus, if you recall, when you first were exposed to trigonometry and the unit circle, our polar coordinate form to look at all of our famous 0, 30, 45, 60, 90 degrees, also known as our pi over 6, pi over 4, pi over 3, pi over 2 radians, uh, our x comma y was on the unit circle. It was just cosine theta, sine theta, because definition of a unit circle, we have that radius is equal to 1. But it really was just looking at our polar coordinate form to rectangular form, vice versa, our r cosine theta, comma, r sine theta, and then we plug in that unit circle or that radius of 1 because it's a unit circle. We have 1 times cosine theta and then 1 times sine theta to get our cosine theta, sine theta. So that's where our conversion really stems from. Okay. And now we're finally on to our example 3. So we are asked to find the rectangular coordinates of the points with polar coordinates. Our part A, again, we're given our polar coordinate form. We have 6 comma pi over 6. And so we know x is equal to r cosine of theta, and then our y is equal to r sine of theta. And then just to recap, our polar coordinate form is in the form of r comma theta. So we have, this is our r, this is our theta, this is our r, this is our theta. And so now we're ready to make the conversion and simplify. So in our part A, our x is going to be, well, if our r is 6, then we have r cosine of pi over 6. And then our y coordinate is going to be 6 sine of pi over 6. And so that was the first sort of tab or first block, first step in the problem. And now let's compute this. Pi over 6 is the same as 30 degrees. Cosine of 30 degrees is square root of 3 over 2. Sine of 30, also known as sine of pi over 6, is just 1/2. So we have 6 times square root of 3 over 2, comma 6 times 1/2. And so that's our second little block revealing. And then let's simplify that. 6 divided by 2 is 3, so our x-coordinate is just 3 square root of 3 simplified, and then our y-coordinate, 6 divided by 2, is just 3. So we get 3 square root of 3, comma 3, and we're done. Let's go a little faster now. Our part B, we're looking at -4 cosine of negative pi over 4, comma -4 sine of negative pi over 4. And we know that cosine functions are even. So cosine of negative pi over 4 is the same as cosine of pi over 4. And cosine of pi over 4 is just square root of 2 over 2. Sine functions are odd, so sine of negative pi over 4 is the same as negative sine of positive pi over 4. And then if we multiply that negative by this -4, this becomes a +4. So now we're essentially looking at -4 times square root of 2 over 2, comma, +4 times square root of 2 over 2. I think that's what's going to be revealed over here. Beautiful. And then simplify that. Negative 4 divided by 2 is just -2. So we have -2 square root of 2, comma, +2 square root of 2. And we're done. Right, let's keep going. Example 4, we have now converting, it's the same thing, just different numbers. Yeah. Uh, we have polar coordinate form, and we're once again asked to find the rectangular coordinates. So part A, we're looking at 4 cosine of pi over 3, comma, 4 sine of pi over 3. Cosine of pi over 3 is the same as cosine of 60, which is 1/2. Sine of pi over 3 is the same as sine of 60, which is square root of 3 over 2. So we get 4 times 1/2, comma, 4 times square root of 3 over 2, which is just reduced to 2, comma, 2 square root of 3. Right? Part B, we have -2 cosine 3 pi over 4, comma, -2 sine 3 pi over 4. And so the reference angle of 3 pi over 4 is pi over 4, but it's in that second quadrant. So sine is going to remain positive, but cosine is going to be negative. And we know cosine of pi over 4 is square root of 2 over 2, but it's really going to be negative square root of 2 over 2 since it's in that second quadrant. Sine of 3 pi over 4 is going to stay as positive square root of 2 over 2, and then it's going to be multiplied by that -2. So there we have that. And let me just make sure I did that correctly, right? Square root of 2 over 2, and it's negative, and that's positive. Beautiful. Yeah, so now when we multiply, a negative times a negative gives you a positive. 2 divided by 2 is 1. We end up with positive square root of 2, comma, negative square root of 2. Great. And then part C, we have our rectangular coordinate point set up as -3 cosine of -5 pi over 6, comma, -3 sine of -5 pi over 6, which the reference angle for that is pi over 6. And -5 pi over 6 ends up in the third quadrant. So both cosine and sine are going to have negative output values. And so cosine of that reference angle, pi over 6, is just square root of 3 over 2, but it's negative. So negative square root of 3 over 2. So that x-coordinate is -3 times negative square root of 3 over 2, comma, and then our y-coordinate is -3 times, and then sine of pi over 6 is 1/2, but it's going to be times -1/2. Okay. Negative times a negative is a positive, and so we end up with +3 square root of 3 over 2, comma, +3 over 2. And we are done. Right. So let's keep going. Now we're on to our third objective, where we're asked to convert from rectangular coordinates to polar coordinates. And so converting from rectangular to polar coordinates, we have the following. Again, if we're looking at our rectangular coordinates, x comma y, our polar is going to be r comma theta. We're very familiar with this at this moment in the lesson. And our r squared is equal to x squared plus y squared. And then we have, okay, we're dealing with a circle centered from the origin. And so our tan theta is just simply our y over our x. Obviously, when x is not equal to 0, because if it is, then we have an undefined value. But if x is equal to 0, then this simply just becomes r squared is equal to y squared, also known as r is equal to y. And then we have a nice quadrantal angle at 90 degrees. Theta is equal to pi over 2. Okay. These are the steps for converting from rectangular to polar coordinates. We have to use the equations effectively. We want to follow these steps. First, we plot our point, and if our x or y are equal to 0, we're going to use the graph to find what our R value is. It's pretty straightforward. It's going to lie on our axes. Now, if our x and y aren't 0, then we're going to use our whole r is equal to square root of x squared plus y squared. And then in order to find theta, if x or y is equal to 0, once again, we're going to use the graph. But if neither of them are equal to 0, then we want to be mindful of where our angle lies, like where the point lies, what quadrant it is. And so if our point or angle measure, we're finding the angle measure. So if our point lies in 1 or 4, then our theta is just arctan of y over x. If our point lies in 2 or 3, then our theta is pi plus our tan inverse y over x. Now, you can also just use the whole all students take calculus as well, and figure out where your angles are positive and negative, and where your trig values are going to be positive or negative. But it'll be easier once we look at concrete examples, which we have now arrived at. Okay, so example 5, we want to convert from rectangular coordinates to polar coordinates. And again, from the previous slide, we have that our r squared is equal to x squared plus y squared, and then our tan theta is equal to our y over x. Our part A gives us the rectangular coordinates 4, comma, -4, which tells us very quickly that we are in our fourth quadrant. Right, our x is positive, our y is negative. And so now let's evaluate what our r is. Our r squared is just 4 squared plus, in parentheses, -4 squared, which tells us that our r is just the square root of 4 squared plus, in parentheses, -4, close parentheses, squared. And that will just give you the square root of 16 plus 16, which is the square root of 32. We can simplify this radical. We can break that up into the square root of 16 and the square root of 2. So we just get 4 square root of 2. Okay, so we have our r in simplified form. Now let's take a look at our tan theta. Our tan theta is y over x, so -4 divided by 4, which is -1. And we know that tan of theta is also the same as sine of theta divided by cosine of theta. So what angle measure can we put into sine and cosine, which will yield the same exact result, so that when we divide it, we get 1, and that's our 45 degrees, also known as pi over 4. But notice how it's negative, so one of them is going to have to be positive and one's negative, which makes sense because we know that our point lies in that fourth quadrant. All students take calculus. Our cosine is going to be positive and our sine is going to be negative. Um, and so we want to look at, okay, what is that? If the reference angle in the fourth quadrant is going to be hitting at 45 degrees, we have negative pi over 4, but if we want to think about it from the positive angle perspective, this is also known as 7 pi over 4. And so sine of 7 pi over 4 is going to give us that negative square root of 2 over 2. And then cosine of 7 pi over 4 is going to give you the positive square root of 2 over 2. Divide the 2, and then you get negative 1. Yeah. I put in the 3 pi over 4 because another way you could have looked at it was that square root of 2 over 2. If I didn't tell you which one was positive, maybe cosine was negative, that would have lied in that third quadrant. So we have these two different values, third quadrant versus fourth quadrant, and then you know that your coordinate point lies in the fourth quadrant. So it's obviously going to be that 7 pi over 4. So finally, our solution in polar coordinate form is just going to be that 4 square root of 2 comma 7 pi over 4. Right. Let's move on to part B. We have negative 1 comma negative square root of 3. Straight off the bat, that's going to go ahead and lie into our third quadrant. We have our R is equal to the square root of, in parentheses, negative 1 squared plus, in parentheses, negative square root of 3, close parentheses, squared. And that ends up simplifying to 1 plus 3 underneath that square root, which is just the square root of 4. And the square root of 4 is just 2. So our R value is 2. Now our tan of theta is y over x, so the square root of 3, or negative the square root of 3 divided by negative 1, which is just tan of theta is equal to square root of 3. And now we want to figure out, okay, what theta values will give us tan theta to be equal to square root of 3. And so again, sine over cosine, this is going to be, I believe, pi over 6, also known as, or sorry, pi over 3, also known as 60 degrees, because sine of pi over 3 is square root of 3 over 2, and cosine of pi over 3 is 1/2. So yeah, you divide the 2 and you get square root of 3 over 1. So from our pi over 3, we want to figure out the different scenarios. We know that it's going to be in that third quadrant. So if our reference angle is at pi over 3 here, we have pi, also known as 3 pi over 3 plus pi over 3. That would give us 4 pi over 3. Which would be our solution here. Yeah, so I don't think I have it circled. Let me circle it. Yeah, and I'm going to X out these. Yeah, so our final coordinate is going to be 2 comma 4 pi over 3. Great. And now part C, we have our 4 comma negative 1, which tells us we're looking at the fourth quadrant once again. Our R is going to be the square root of 4 squared plus, in parentheses, negative 1 squared, which is just 16 plus 1, which is 17. So R equals square root of 17. And now our tan theta is going to go ahead and be our y over x, which is negative 1 over 4. And we can do this two different ways. we know tan is an odd function, so we could write this if we wanted to find our angle value. Let's see. Yeah, so we know tan is an odd function. So when we take our angle theta value, our theta is arctan or tan inverse of -1/4, but because tan is odd, we can pull out the negative and we can look at it as negative um, tan inverse of 1/4, which is what we have here. Or we can use what they were stating in our notes over here. Um, because oh no, I don't think we had any. Yeah, never mind. I was thinking of this, but no. Um, Another way you can just write it from the positive perspective is to add our 2 pi to it. So we have, or our theta is equal to 2 pi minus our tan inverse of 1/4. Uh, and then, eh. And so our final coordinate would be where'd it go? Over here. Yeah. Our final coordinate is going to be square root of 17, comma, negative tan inverse of 1/4. And we are done. So that was example 5. Let's keep going. And now we're on to our 4th objective, being able to transform equations between polar and rectangular forms. So just to recap, we have x is equal to r cosine theta, y is equal to r sine theta, our r squared is equal to x squared plus y squared, and our tan theta is equal to y over x. These are the equations that we use in order to transform from rectangular to polar or polar to rectangular. And so the 2 common techniques for transforming from these forms is to multiply both sides of the equation by r so that we can maybe utilize some substitution later on, or to square both sides of the equation so we can once again utilize some substitution later on. So now we're going to go ahead and practice that. So I'm going to first write out all of our equations from our previous slide. Our good old r cosine theta and r sine theta is equal to x and y respectively. Our r squared is equal to x squared plus y squared. And then I'm going to keep that other purple one covered just because I'll reveal it later on. And so we are asked to transform this equation r equals 6 cosine theta from polar to rectangular coordinates and then identify the graph at hand. And so let's take a look at this x squared plus y squared equals r squared from this perspective with our x's and y's. And when we do that, we get r squared cosine squared theta plus r squared sine squared theta. And we know, oh, a Pythagorean identity, cosine squared theta plus sine squared theta is just 1, is equal to our r squared. Well, what is r squared here? R squared is just our 6 cosine theta times r. Okay. Let me try and reveal these. And so, yeah, let's factor out that r squared on that left-hand side. Oops, don't know where that came out of. And when we do that, we get r squared in parentheses cosine squared theta plus sine squared theta is equal to 6r cosine theta. And that cosine squared theta plus sine squared theta is just 1. Now, notice this r over here is where we are going to reveal that last purple thing. R is just the same as x over cosine theta. Just get r by itself. And so when we plug that in, these cosine thetas cancel out and we're just left with 6x. So essentially, we're just looking at r squared is equal to 6x. Now, is there a much easier way to do this? Yes. And so let me show you really quickly how you can get that without doing all of these crazy substitutions. Go back to what they said with the hints. The two common techniques, multiply both sides of the equation by r, or square both sides of the equation. Let's just multiply both sides of this equation by r, and when we do, we end up with r squared is equal to 6r cosine of theta. But we know that r cosine of theta is x. So we once again get r squared is equal to 6x. Nice and simple. Okay. Let's keep going. So now we have our x squared plus y squared is equal to 6x. And now we're starting to see what's happening here. We have a circle that we're dealing with. We want to bring everything over to that left-hand side, set it equal to 0, and then complete the square in order to figure out what is the center point of this circle and what is the radius. So now we're looking at x squared minus 6x plus y squared is equal to 0. That special key, we want to divide that negative 6 by 2 and then square it. So we have negative 3 in parentheses squared is that special constant 9 that we want to add to both sides of the equation to keep it balanced. And so that x squared minus 6x plus 9 can now be completed into our x minus 3 in parentheses squared. And this y squared is just the same as y minus 0 in parentheses squared. That was the special key stuff. So now we're looking at x minus 3 in parentheses squared is equal to, I don't know why I wrote 9 minus y squared. I should have, let me rewrite this. Maybe I have it up here. Yeah. I don't know why I had that as. It was weird that I brought that over to that side. I'm going to change that. All right, that's better. And then I put the 3 stars here just to show the continuation. And so that y squared, like I said before, is the same as y minus 0 in parentheses squared, so that we can clearly see that we have a circle with center point 3 comma 0 and a radius of 3. And so now we officially identified our graph, and that completes this problem. So we'll be doing some more examples just to get the hang of everything. All right, covered up that answer again. So now we are doing the opposite. We want to transform an equation from our rectangular coordinates to polar coordinates. And so this part is actually incorrect over here. Let me fix that. Okay. It's correct in the problem though. Transform our equation for xy is equal to 9 from rectangular coordinates to polar coordinates. And here you can actually very clearly identify the graph off the bat. We have, let's see, let's divide both sides by 4x. And when we do, we get y is equal to 9 divided by 4x, which is a nice reciprocal function, our famous reciprocal function 1 over x. So we're looking at nice rectangular hyperbola for our graph. Okay. But now let's transform this into polar form. So our nice substitutions, we have our x is equal to r cosine theta, our y is equal to r sine theta, and then we have the good old x squared plus y squared equals r squared. And so wherever we see an x, we're going to change it to r cosine theta. So we have 4 times r cosine theta times our y, which is r sine theta, is equal to 9. And this is the same as 4r squared cosine theta sine theta is equal to 9. And that cosine theta sine theta, we can use our double angle formula. Our sine of 2 theta is 2 cosine theta sine theta, which I have off to the right over here, also known as 2 sine theta cosine theta. And so we want just one of this. So why don't we go ahead and divide this whole thing by 2? So we have 1/2 sine of 2 theta is equal to our sine theta cosine theta, also known as cosine theta sine theta. And so now what I have highlighted in green, we can make that substitution in over here. And when we do that, we get the following. And we can simplify. This 4 on the outside goes into 2 twice. So now we're looking at 2r squared sine 2 theta is equal to 9. And then let's go ahead and divide both sides by 2. And so we get r squared sine 2 theta is equal to 9 over 2. And then last but not least, let's divide both sides by sine 2 theta. So our r squared is just simply 9 over 2 sine 2 theta, which once again, we already figured out from the beginning of the problem that we are looking at a hyperbola, more specifically a rectangular hyperbola. Yeah. And then I don't know what was there. This was nothing. Just an imaginary little cover up. And yeah, so that completes this problem. Right? So let's keep going. We have identify and graph polar equations by converting to rectangular equations. And so this slide is just talking about how, just like we use our regular XY coordinate plane to graph our XY coordinate points on a very easily readable graph, we can do the same with plotting polar coordinates on a graph that contains those concentric circles so that we can easily plot what our radius is as well as our angle measure. And I showed you guys this in our example 1, so I was sort of like foreshadowing up to this slide. And these are known as polar grids, and they're very, very useful for plotting our polar coordinates. Maybe I'll highlight the polar grids word to coincide with our polar grid down below here versus our good old rectangular grid. over here. These are points used on a rectangular grid, whereas these are points used to plot on our polar grids. Okay. Formal definition of a polar equation is an equation whose variables are polar coordinates. And the graph of a polar equation consists of all points whose polar coordinates satisfy the equation. So one method that can be used to graph a polar equation is to convert the equation to rectangular coordinates. And then in the following discussion, xy represents the rectangular coordinates of a point P, and r comma theta represents the polar coordinates. So things we've seen before. Right, and now we are on to our example 8, where we are identifying and graphing a polar equation, and we actually have a circle here. So they give us a nice little hint. So we have our equation r squared equals x squared plus y squared. But when we're looking at r is equal to 3, it's quite clear we have no theta value here. And because we have no theta value, our constant distance is just straight 3 from the origin. And so this is going to be quite straightforward to plot. We're looking at our circle with a radius of 3 from the origin. So it's just going to go up 3, down 3, to the left 3, and to the right 3, and then connect the dots and plot our circle. And we are done. Okay. Let's look at example 9, where now we are given theta. Theta is equal to pi over 3. And so we can look at our tan theta is equal to y over x. And so that's the same as theta is equal to tan inverse of y over x. Or when we plug in our theta for pi over 3, we can just write it as tan pi over 3 equals y over x. And I sort of showed the answer. But pi over 3 is the same as 60 degrees. So, and tan is the same as sine over cosine. So what's sine of 60 divided by cosine of 60? Sine of 60 is square root of 3 over 2. Cosine of 60 is 1/2. So tan of pi over 3 is just square root of 3 over 2 divided by 1/2, which just gives you square root of 3. And I'm foreshadowing. How do I cover this up again? And so if you know your tan pi over 3 is square root of 3, but you also know it is equal to your y over x, we can look at y over x is equal to square root of 3, and then multiply both sides by x, and you get y is equal to square root of 3 times x. And that was that last part. And that's very helpful because now we can very clearly identify the graph. We have a linear function at hand. And so our angle is constant at our pi over 3. And so with no restrictions on r, we have a straight line, kind of showed it numerically over here, going through the origin. Okay, so let's graph this. It's just a nice little sketch where we have y is equal to square root of 3 times x, and this angle measure here gives us that 60 degrees. And we're done. right? Let's keep going. Our example 10, we want to identify and graph r sine theta is equal to 2. We know r sine theta is the same as y, so we're just looking at y is equal to 2, aka horizontal line. And so that's, again, very straightforward to graph. There we have it. Whereas example 11, we're going to probably look at the opposite. Nice vertical line. Our cosine theta is the same as x, so we're looking at x is equal to -3, which is a nice vertical line. And again, quite straightforward to graph. Okay. So this is just telling us whenever you have like r sine theta is equal to some numerical value, we're going to be dealing with y is equal to some numerical value. So we have a nice horizontal line that's taking place. Whereas when we're dealing with our cosine theta is equal to some numerical value, then we have x is equal to some numerical value, so a nice straightforward vertical line is taking place. I believe we only have 2 more examples. So we are asked to identify and graph the equation r is equal to for sine theta. I give you a hint. We're going to be looking at a circle here. In this case, let's use that first method again, multiplying both sides by r. And when we do that, we get r squared is equal to 4r sine theta. And then we're going to substitute that into our r squared equals x squared plus y squared. And when we do that, we get 4r sine theta is equal to x squared plus y squared. And y squared, if we square this, we're looking at r squared sine squared theta. But it actually might help to just keep everything in terms of x and y so that we can put it into our general equation of a circle form. And so that r sine theta is the same as y, and then this r squared sine squared theta will bring it back into our y squared form. So we get 4y is equal to x squared plus y squared. Let's bring everything over to that right-hand side, set it equal to 0 on that left-hand side, and do some completing the square in order to identify what our center point and radius are. So we get x squared plus y squared minus 4y is equal to 0. And then using the special key, that -4 divided by 2 in parentheses squared gives you -2 squared, which is plus 4. And so that's what we are going to add to both sides so that we can now complete the square for our y quadratic function. And that just factors into y minus 2 in parentheses squared. Our x squared factors into just x minus 0 in parentheses squared. And then 4 is the same as 2 squared. So, oops. So we get x minus 0 in parentheses squared plus y minus 2 in parentheses squared equals 2 squared, which very clearly shows that our center point is at 0, 2 with a radius of 2. Okay. And again, we have a circle. We just proved it. Now, how do we graph this? Well, our center point is at 0, 2. Plot the center point first, and then go up, down to the left, to the right 2 units. Plot those additional 4 points, and then create your circle. And we are done. One more example. Our example 13, we're once again asked to identify and graph the equation r is equal to -2 cosine theta. And so we have our x is equal to r cosine theta, our y is equal to r sine theta. The method we're going to use here is to multiply both sides by r. So we're now looking at r squared is equal to -2r cosine theta, but r cosine theta is the same as x. So we can substitute that in and we get r squared is equal to -2x. Replace that in our equation, r squared is equal to x squared plus y squared, and we get -2x is equal to x squared plus y squared. Bring everything over to that right-hand side and complete the square. We get 0 is equal to x squared plus 2x plus y squared, and that special key is the b over 2 in parentheses squared, which is our 2 value here. 2 divided by 2 is 1, and 1 squared is 1. So 1 is that special constant that we're going to be adding to both sides to balance, keep the equation balanced. And now we can very easily factor x squared plus 2x plus 1. That's just x plus 1 in parentheses squared. That y squared is just y minus 0 in parentheses squared, and then it's equal to 1 squared. Can very easily identify that we're dealing once again with the circle. We have a center point at -1, 0 and a radius at 1. So when we graph this, we graph our center point first, go up 1 unit, down 1 unit, to the left 1 unit, to the right 1 unit, plot those 4 points, create your circle, write the equation of the circle, and we are done. So this is just a slide kind of like summarizing everything. If you have your equation r is equal to 2a sine theta, then our radius is going to be a, our center is going to be 0, a, and then if it is negative, then our center point is going to be negative. If we were dealing with cosine instead of sine, then our points are going to be flipped. Instead of it being 0, a, it's now going to be a, 0. And then again, if it's negative, then it is going to be negative. So yeah, this is sort of like a cheat sheet to help you save some time. And yeah, this is an overview of our rectangular equations, polar equations, and dealing with our vertical lines, our horizontal lines, our lines that pass through our origin. That tan of theta is equal to y over x problem that we solved a few problems back, and our circles that we are quite strong with at this point. So yeah, this is the last slide, and it completes the lesson for today. So I hope this was helpful. Let me know if you have any questions, and I'll see you guys next time. Take care. Bye.